All right, we are looking at section 10.2 today. That is slope fields. Slope fields is actually a topic that AP added to the AP exam just a few years ago. It's the only topic that I know of, well, at least since I have been teaching, that is an added topic. And so it has extra significance. It has shown up more often on the AP exam than perhaps other things because it was recently added. And when AP added the slope field topic, they gave us a handout that covered the 4 things that they wanted students to be able to do. So rather than teach you this section from your textbook, it is in your textbook, but I'm going to teach it to you from the handout that AP gave. So according to AP Central, these are the 4 things that they want you to be able to do with a slope field. You should be able to sketch a slope field for a given differential equation. Now that's the same thing that we were just doing in section 410 with our fields. You should also be able to match a slope field to a differential equation that they graph for you. So that would be the same thing as number 1, only they would do the graphing for you. Number 3, given a slope field, sketch a solution curve through a given point. That's what we were doing as well when they would tell me to start at, for instance, like 0, 2, and then we would follow the direction field or the slope field to sketch the graph. And then the last thing is match a slope field to a solution of a differential equation, which we have not specifically done before. So name a function that you get from taking the antiderivative of 2x. Yeah, basically you could come up with a variety of different things. You could get x squared plus 5, x squared minus 7, x squared plus 3,254.6. Basically, you're going to get x squared plus c because the antiderivative of 2x is x squared plus c, where c could be any constant. So if you were to graph those, you would create a family of antiderivatives. For instance, here we've got y equals x squared plus 2, x squared minus 4, something like that. That is the graph of the family of antiderivatives that go along with that function. So on your handout for number 4, they tell me that dy dx is equal to 2x. Another way that we could show the family of antiderivatives associated with 2x is, instead of actually calculating the antiderivative and graphing the equation, we could draw a slope field for 2x. Since dy dx is equal to the slope, when we plug in an ordered pair into that equation, what we are getting is the slope because derivative is slope. So let's start over here at x equals -3. You'll notice that in this function I don't have a y value, so it doesn't matter if I plug in -3,2 or -3,1 or -3,0. I'm going to get the same answer every single time. When I plug -3 in for x, I'm going to get -6. Now, how do I know how to graph -6? Well, I'm going to approximate a slope. I'm just going to pick a segment of a line and say, okay, 1, 2, 3, 4, 5, 6, and then I'm going to go over that same distance. So I went down 6 units and over 1, and then I can just kind of sketch what I think that slope would look like from that all the way along here. Same idea if we go through and we plug in -2. If I plug -2 in for x, I get -4, so I can do that same sort of thing. And you'll notice that I still have a negative slope here, not quite as steep as the one I had a second ago. Plug in -1 and I get a slope of -2, so same idea. And again, a negative slope, but not quite as steep. Plug in 0 and I get 0, so I'm going to have horizontal lines all the way along there. And then we continue with that same idea. Plug in 1 and you'll get a slope of 2. Plug in 2, you get a slope of 4. Plug in 3, you get a slope of 6. So here is my slope field for that function. Now notice that all the points that have the same x coordinate have the same slope because there's no y term in the equation. Now that wouldn't always be the case. In this equation we only had an x. If we had had an x and a y, then things would be different. But that's going to be a big help to us when we get to matching our formulas, if we recognize that if we have the same x coordinate, we have the same slope. So keep that in mind. All right, let's look at another one. Oh, sorry, one thing. If they had told me to start at 0, then I would have started at 0 and I would have followed that slope field or that direction field. If they had told me to start at -2, I could have done the same thing. So here is the powerful thing about a slope field. Even without knowing the equation of the antiderivative x squared, you'll notice I just graphed x squared plus 0, x squared minus 2. I literally just was able to graph those values. And so the same way that up here we calculated the antiderivative, down here we didn't have to calculate it. So as we just saw, some differential equations can be solved and then graphed algebraically, and the slope field can then be used to verify that that algebraic solution matched the graphical solution and was right. But other times the differential equation may not be able to be solved algebraically, and the slope field provides a way to still be able to solve it graphically. Okay, so here's another example. Let's look at number 2. We've got the derivative is equal to 2y. So if I go through and I plug in values, notice that it doesn't matter if I plug in -3, +2, or -2, +2, or -1, +2. When I plug in +2 for y, every one of those slopes is going to be the same. It's going to be a slope of 4, and you've already got there on your paper what a slope of 4 would look like. Then we could plug in +1 and we'll get a slope of 2, so we'll graph all slopes of 2 along here. Then we could plug in 0 and we'll get a slope of 0, so horizontal lines all across there. And then plug in -1 and -2 and we'll get slope of -2, slope of -4. Now again, notice our shortcut. Notice that all the points that have the same y coordinate have the same slope, and that's because there's no x term in this equation. So again, that's not always going to be true, but when I get to the matching, that'll be a big clue for me to help match my functions with the slope fields. All right, look at another one. For number 6, this is the first one where we have both an x and a y. And so when I come over here to -3, +2, and I plug in that point, the slope that I get is going to be different from if I plug in, say, -3, +1, or -3, 0. So I'm literally going to have to evaluate point by point. So I'm going to plug in and get +2/3, and then +1/3, and then 0. I can, however, look for shortcuts instead of sitting here and plotting point by point by point. I could pick up some shortcuts, like I got a clue right here from this slope of 0 we got a second ago. Notice that anywhere my y value is 0, that's going to give me a slope of 0, except for when the denominator was 0. So I could go through then and say, okay, anywhere I have a y value of 0, I'm going to have a slope of 0. We also got a clue from what we said a second ago. I wouldn't want to have 0 in the denominator. Why? Well, because anywhere x is equal to 0, that gives me 0 in the denominator. All of those values are going to be undefined. So I just filled in all of these values across here as 0 slopes and all of these values here as undefined slopes, which in a graph would typically cause a vertical asymptote. Another thing that would help is to think about where y and x are equal to each other. Because in this equation it's y over x, anywhere y and x are the same value, I'm going to get a slope of -1. And anywhere they're opposites of each other, like let's say +3 and -3, anywhere they're opposites of each other, I'm going to get a slope of +1. So you can see the diagonal here that has slopes of -1, and you can see the diagonal here that has slopes of +1. So although we do have to sit here and plug in values for each of the other points, you'll notice that we do have shortcuts that we can use on many of them. All right, so the second thing we want to be able to do is, what if they do all that work of drawing the slope field for me? I need to be able to then match the derivative to the slope field. So again, since dy dx is the same thing as the slope, when you plug x, y into the equation, you get the slope at that point, and the slope is what is graphed. So when I start with 15, I could go through, and again, I can plug in points and sit here and just do point by point by point, but I'd really rather look for some shortcuts. Remember when we had the problem that did not have a y value in the equation, and when we had no y term, all of the segments in a vertical direction had the same slope. So that's going to be a good indicator for me here. If I go through and look at these, out of all 4 of these graphs, there's only one of them that all the segments in the vertical direction have the same slope. So we could then use that same idea as a shortcut for number 16, where we only have a y value and we don't have an x value. What would the shortcut for that one be? Since there's no x term, all segments in the horizontal direction would have the same slope. So you can go from there in terms of figuring out which of those graphs that would be. All right, look at 17. For number 17 and 18, I have an x and a y. And you'll notice, sure enough, up here out of my 4 graphs, there are only 2 of them that don't have that thing where all segments in a horizontal or vertical direction are all the same. So that has narrowed it down a little bit for me. So if I'm looking at x minus y, again, I can sit here and plug in points, but I'd really rather look for some shortcuts. Some of the shortcuts might be, if x equals y, then my derivative is 0. So anywhere I have like x is 1 and y is 1, 1 minus 1 would give me 0. So I can come over here and say, on these graphs, first off, this one has the vertical lines that are the same, and this one has the horizontal lines that are the same. So we've already ruled those out. Out of these 2, these are the ones that don't have all the horizontal and vertical slopes the same. So that means they have both an x and a y value. Out of these 2, I can go through and say, where does x and y, when they're equal, give me a slope of 0? Well, you can see 0, 0, 1, 1, 2, 2, 3, 3, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3. So that graph is going to match up to C. And then that just leaves us with this last one down here to work with in matching. All right, so the next thing that they want us to be able to do is to draw a slope field for a given differential equation. So for number 19, they've gone through and they've created the slope field for us, and they've even gone through and drawn one of the solution curves that passes through 0, 1. So basically start at 0, 1 and follow our slope field or our direction field. So we want to do the same thing now at 0, 2 and at 0, negative 1. So if we start at 0, 2 and we follow that direction field or that slope field, we're going to end up with another parabola that looks a lot like the one we had a second ago. But if we start at 0, negative 1, our parabola is not going to look the same. That parabola following the direction field is going to open down instead. All right, and then the last thing that we want to look at, we tend to make harder than it is. For this last one, it says match each slope field with the equation that the slope field could represent. And if you look at your equations, it's not dy dx equals, it's just y equals. There is no derivative here. There's no derivative to take, there's no integration to do. Literally, I'm just matching a slope field to the solution of the differential equation. So let's say if you wanted to match dy dx equals 2x to its solution, the solution of that would be y equals x squared plus c. So basically what I'm doing is looking down here at these graphs to see which one of those could be the graph that coincides with y equals x squared plus c. And we'll actually catch that one down here in number 9 in just a second. So basically we would know how to match without having to create a point-by-point slope field. All right, so let's look at number 7. Which one of these could be the slope field that goes with y equals 1? Well, y equals 1, of course, is a horizontal line. So the only one of those that could match would be D. All right, let's look at number 9. This is the one that we were referring to up here a moment ago. If I've got y equals x squared and I look at these, which one of these slope fields would yield a parabola? Well, that, of course, is going to be C. All right, look at number 11. For 11, we've got 1 over x squared, and we're trying to say which one of these would match with 1 over x squared. If you're not sure what that graph looks like, you could always make a little xy chart and sketch the graph of it, or you could work with it in its slope field, either one. But the graph of 1 over x squared looks like this guy up here, so that matches with A. Okay, so what does this actually look like on the AP exam? Here's a problem from the 2004 exam where it says, consider the differential equation on the axes provided, sketch a slope field just for these 12 points. So I can go through and I can start over here with -1, +3, and I'm literally going to plug that into the equation, put in -1 for x and put in 3 for y, and I end up with a slope of +1. Then I could go through and plug in -1, 2. And when I do that, I get a slope of 0, and that should be like a flashing light to me that there might be a shortcut associated with that. Then I could plug in -1, 1 and -1, 0. And so I've got this whole first column here. All right, if we go back to this idea that we had here in terms of looking for a shortcut, I got a slope of 0 because I ended up with this second value being 0. That second value came from y minus 2. So anywhere y equaled 2, I would get 0 for that second value. So every one of these right here where y equals 2 is going to be a horizontal line. That's going to be one of my shortcuts. That also kind of leads me to think about, okay, how could this first value become a 0? Because 0 times anything is 0. Well, anywhere x equals 0, then I would get a slope of 0 as well. So that would also be another shortcut for me where I could say, okay, at any 0 value, all of these are going to be a slope of 0. Then if you'll notice, when I come over here and I start plugging in, when I plug in 1, 3, I get the same slope of 1 that I got when I plugged in -1, 3. And I recognize that when I take -1 to the 4th or I take +1 to the 4th, I'm going to get the same thing. So in essence then, every one of these values over here are going to be the same as the values I've already calculated over here. So typically on these problems, they are going to give you some shortcuts so you don't have to calculate 12 different values. Additionally, on the AP exam, when they score this, they're very generous in that they want to see that you have 0 slopes in all of the appropriate places or undefined slopes. But otherwise, they're not real picky about, is this a slope of +1 or of 1/2 or of 1/4 or of +4? Basically, if it is going in the positive direction, then they're going to give you credit for it. If it's going in the negative direction, they're going to give you credit for it. On my test, I want to see a difference. I should see a difference between 1/2 and +4. And obviously, I should see a difference between a positive slope and a negative slope. So not that you got to get a ruler out and measure or anything like that, but we do want to be precise. Okay, then the second thing they say down here is, while the slope field in part A is drawn at only 12 points, it's defined at every point in the xy plane. I mean, you look at this derivative, there's nowhere that it doesn't exist. I don't have a 0 in the denominator or negative under a square root or something like that. So it says, describe all points in the xy plane for which the slopes are negative. So is there any way that I could get a negative slope from this first piece? Well, no. We saw here a second ago that when you put a negative number in or a positive number in for x, you're going to get a positive value. So the negative is going to have to come from this piece. It's going to have to be wherever y minus 2 is negative. So I can just say then, okay, where is y minus 2 negative? Where is it less than 0? Add 2 to both sides, and I'll get y is less than 2. So I can kind of verify that on my graph over here because I can see where y is less than 2. Yeah, these slopes are negative. These slopes are negative. These slopes are not negative. Why? Well, because that's where x is equal to 0, and that caused a 0 slope. 0 is not negative. So I must make that exclusion down here that x can't be equal to 0. So it's when y is less than 2, but also when x is not equal to 0, they would be looking for that exclusion to give me full credit. All right, the last thing down here says, find the particular solution, y equals f of x, to the given differential equation with this initial condition. We do not know how to do this yet. These are called separable differential equations. It's actually the last topic that we will look at before the AP exam, so it will be fresh in our mind. But I just want to give you a little bit of a heads up on it while we're here today, because typically when one of these slope field problems comes up on the AP exam, Every FRQ is worth 9 points. Typically, 6 of the 9 points are right here. So they'll give you usually 2 points for A, 1 point for B, and then 6 points for C. So let's just talk about the idea of that separable differential equation with the understanding that we will learn it later on. If I have dy dx and I literally think of that as a differential, like a fraction, then I could go through and separate this differential equation. I could separate it so that I would have all the y's on one side and all the x's on the other side. Why would I want to do that? Well, notice they want me to give y equals f of x, and what I have right now is dy. I have the derivative. I want to go back to the original. To go back to the original, I have to integrate. I can't integrate y and x at the same time. I can't integrate y and x at the same time. So what I want to do is get all my y's on one side and all my x's on the other side, so that then I could come down and integrate everything in terms of x and integrate everything in terms of y. So up here we multiplied both sides by dx to get it over here, and we divided both sides by y minus 2 to get it over here. We do not know how to do this integration yet on the left-hand side, but we do know how to do the integration on the right-hand side, and we get an arbitrary constant. Now, we've seen this before where if they give me an initial condition, that I can plug that in and solve. And so even though we don't understand all of the work that is going on with the integration, I do know how to undo a logarithm by using an exponential. So I can insert an exponential on each side. And when I do that, I'm left with the absolute value of y minus 2. To get rid of that absolute value, remember that when you have an absolute value equality, you get rid of the absolute value bars by putting a plus or minus in on the other side. Then I could do a little bit of simplification with putting in that ordered pair 0, 0 and solving, and I'll be able to come up with a value for k that I could back substitute, add 2 to both sides, and then I've got an equation for y. So again, that's not something that we know how to do yet, but something we get an idea of. All right, so for tonight, we want to finish this packet that I've given you. We've done half the problems. You want to go through and do the rest.